So I asked Jerry, because he always makes me laugh every time we do a bio. He said tonight all he wants to say is he's retired for the final time after 3 tries.
Three tries.
So
Three tries.
uh, we've the spiral curves came up. Let's see, through Wisdom Wednesdays, right? When we were one of the
Yeah,
chapters,
we're
one of the
talking
chapters on
about
Wisdom.
curves and descriptions and
Yep,
stuff. Yeah.
exactly. So this is kind of a no point intended spiral off of Wisdom Wednesdays that we were talking about curves and descriptions and that kind of stuff. And so we thought Jerry thought it would be nice to have a presentation on this. And so I know it's always hard when we're dealing with railroads and drawing them and all that kind of stuff. So we wanted to put a little presentation together about spiral curves. So for the third and final time, retiree, Mr. Jerry. I love
Okay,
it.
let me share my screen.
You should be, yep, you should be good. And then in the chat, I'm going to throw the link to Jerry's presentation, the handouts, the homework assignment that you all did.
Yeah, I should collect. I'm gonna be collecting that. Your handles in. I was collecting assignments at the beginning of the sessions. But okay. Mentoring Mondays, Jerry Mahun, PLS. My email is there, as is my website, and a lot of this stuff is on my website that I presented on technical stuff is here. Tonight, we're going to be talking about spiraling out of control. All right. Like Trent said, this came up back when we started talking about curves and descriptions in the discussion of Waddell's Writing Legal Descriptions textbook back in November, I think it was. And we had some on and off discussions about particularly railroad curves and that type of thing. And I thought, well, maybe we could put some stuff in with respect to highway curves, because that's a knowledge area for the PS exam for people that are taking it. And I don't know how many people are still teaching spirals and stuff in school, but I thought I'd just touch on it a little bit. So to kind of frame this, instead of just diving in on the math on stuff, we're going to talk a little bit about background, why we even talk about spirals, or why they're even under consideration. What is the geometry behind a spiral, and then ways that we can do spirals by deflection angles, and a couple of examples. And then I have a spreadsheet on my website that shows the different ways of computing the spiral using the 5-chord to 10-chord method, which I'll talk about here tonight. So basically, the reason spirals exist is because of vehicle dynamics. A spiral, a circular curve, is got a constant radius, whereas a spiral has got a constantly changing radius. So it starts out at a radius of infinity at a tangent, and then gets sharper and sharper the further you go into it. Now, a spiral is a relatively complex curve, particularly when you use a large part of it. It's sort of like when we look at parabolas or second-degree polynomials that we use for vertical curves. A second-degree polynomial can be a relatively complex curve, but when we use them in a vertical curve, we only use a small piece of them. So we can simplify some of the geometry and some of the calculations because we're using small pieces of them. And as it turns out, what we need spirals for, we don't need really long spirals. So there's some approximations we can use and still come out with some pretty good results on spirals adopted in the curves. But again, it all goes back to basic vehicle dynamics. And this goes all the way back to physics and stuff. And whether you want to argue whether it's called centrifugal force or centripetal force, I don't care. Come down on whichever side you want. But as the body travels a curved path, there's a force pushing out on it from the center of curvature from that path that it's traveling. And that force is centrifugal force, and it's a function of velocity and radius. So if we hold the radius fixed, but change the velocity of the vehicle going around that curve, it'll experience higher or lower amounts of centrifugal force. The slower you go, the less centrifugal force. The higher you go, the greater centrifugal force. What the designer has control over is the radius of the curve. he has no control over how fast somebody's going to drive. I mean, we can put up speed limit signs, but those are just basically crude suggestions for people that they're welcome to ignore at their peril and that type of thing. But basically, the only part that we have control over as designers is the radius. So as velocity increases, centrifugal force increases. As radius decreases, centrifugal force increases. So it's a matter of comfort. And one of the ways that we use to offset that force acting on a vehicle to kind of assist the driver in negotiating a curve is to use superelevation. Everybody knows what superelevation is we tip the pavement towards the inside of the curve, and we use part of the vehicle's mass to help offset that centrifugal force. So when a car goes around a curve, we're using the superelevation and the friction factor of the tires in contact with the pavement to kind of counterbalance that centrifugal force acting on it. Now, the tire friction and the superelevation rate together define a speed range for a curve, which we'll talk about in a second or so. When we're on a tangent section, the radius is equal to infinity. And there was a typo in the handout. I think I had radius equals 0 in there, or on the PowerPoint slides I had on the website. That's supposed to be radius equals infinity. The centrifugal force acting on a vehicle is equal to 0. Now, on a traditional horizontal curve, where you're going into a circular curve, technically, right at the point where the curve begins, you're in a full radius situation. So theoretically, instantaneously, you have the full centrifugal force acting on the vehicle at the beginning of the curve. Well, that's generally not the case because a driver is in control of the vehicle and has to make a decision on when to start turning the steering wheel angle to turn into that curve. So as you're turning into that curve, you're actually decreasing the radius of the traveled path and increasing the centrifugal force. So the driver is compensating to a certain extent with respect to that. And we also get around by using flatter curves. The flatter the curve is, a low degree of curvature or a very high radius, the less centrifugal force action we have acting on the vehicle. So a curve has got a speed range where we've got the friction acting with the superelevation to offset the centrifugal force. That's the maximum speed that a curve can handle. If you got the friction, the superelevation is too high for centrifugal force, then you have the friction acting against the superelevation to keep the car on the curb. You can think about it as if you come to stop on a super elevated section, there's enough friction there that keeps your car on the pavement without sliding to the inside. But if you've ever driven in Wisconsin and you stop like that on an icy surface, you're slowly going to slide to the inside of the curb because you got too much super elevation and no centrifugal force to counteract it. So that defines a speed range for a curve. So that's why we can state, speed limit 65 miles an hour, but somebody can go through it safely at 75 miles an hour because there's that safety factor built in based on that speed range. There's also what's known as a hands-off or an equilibrium speed. And that happens when the velocity is, when the super elevation rate is offset by the centrifugal force alone, and the tire friction doesn't come into play. So if there's a certain speed, you can drive around a curve, and that curve can be perfectly frictionless, friction-free. It can be icy or oily stuff. Your car won't slide to the outside and won't slide to the inside because the forces are perfectly balanced on it. And I used to talk about that in my classes, but I had too many students who would go out there and experiment with their cars and try to find what the equilibrium speeds were for different curves and stuff they're on. So we but the car kind of drives itself around the curve because all the forces are balanced on it. And you can kind of think of it as when you were a kid riding a bicycle and you took your hands off your handlebars and you tipped yourself to go around curves and stuff like that. That's what you were doing, is you were establishing equilibrium, offsetting the curve with the centrifugal force acting on your body. And so that's not necessarily halfway in between these two guys, but it's one that we take into account when we're designing curves and stuff. All right, so if we put in a spiral that's got a constantly decreasing radius, what happens is we start with, at the tangent, no centrifugal force acting on the vehicle. And as we go further and further into it, the centrifugal force starts to build up, starts to get larger and larger and larger. So at section AA, we've got flat pavement and our steering wheel is straight ahead. As we move into that curve, we can start introducing the super elevation and start turning the steering wheel to balance the forces till we reach full super elevation at the end of that curve. Now we can hold it through the rest of the curve. So instead of going instantaneously from no super elevation to full from no centrifugal force to full centrifugal force, we can introduce this distance that allows us to put in that super elevation, because otherwise, theoretically, you'd have to do it almost instantaneously. What a lot of departments of transportations use for lower speed situations where they're not using spirals is they use a 2/3, 1/3 rule for introducing super elevation. They start 2/3 of the transition distance before the curve and continue it to 1/3 of the transition distance onto the curve. So they start introducing super elevation rate, but it's not fully there until you're already onto the curve. So at certain points, you're depending on the friction working with and against super elevation to keep you on the road. But a spiral takes care of all that, and it just introduces it gradually. And to the driver, the car more or less kind of drives itself around a curve because it's a gradual going through the curve. Now, when we talk about trains where spirals are used extensively, there's different dynamics with trains. With a car, you've got a driver that's in charge of steering the vehicle, and he makes the decision of where to place that vehicle in the lane. And you've got the friction on the tires that can slide in or out and all that kind of neat stuff. Well, on a train, you actually have a mechanical connection between the train wheels and the track. So you think of it as infinite numbers of friction. There is no sliding in and out and that type of thing. And the engineer doesn't have a big old steering wheel up there. He steers that around the curve. He follows the track. So what happens is if we lay in a curve in a circular arc and we pass a train over that, over time, what happens is that track moves into a spiral configuration because of the forces acting on that train. Well, rather than let the train decide where the track is going to go, we kind of design it that way to begin with. So we lay them in spirals to begin with, which is why in rail, whenever you're dealing with high-speed rail, and a high speed for rail, we mean anything basically over 30 or 35 miles an hour, we have to put in spiraled curves in order to fully balance the forces acting on the train. Okay. All right, so we use transition spirals. A transition spiral is an entrance is identical to the exit spiral. They're basically mirror images of each other. So if we're using the entrance spiral to introduce super elevation coming into a curve, we use an identical one, but backwards to take it back out again. So we're transitioning along this directional change, getting sharper and sharper and sharper, and flatter and flatter and flatter until we're back on a tangent section. Now we could use full spirals coming in and coming out. It's more complex to compute because they're longer and we're using more of the spirals, so we got to take into account the full geometry of a spiral curve. Or generally what we do is we use a circular arc for the transition for the bulk of the curve, and we use a short transition spiral to introduce the super elevation coming into that curve, and then another exit spiral to take that out. So we'll transition into it, get our tighter steering wheel angle, maintain it all the way around, and then start bringing it back out again. So as a result, our spirals are relatively short. And that's what allows us to use some approximations on them and get away with that stuff. How short? Well, this is from the Wisconsin Department of Transportation Facilities Design Manual that all the engineering firms use for the route design. And most DOTs, excuse me, have these kinds of standards in that. This is for a maximum super elevation rate of 6%. Okay, so the sharpest curve could be at a 6% super elevation rate. is 2,040 feet, which is a pretty sharp curve. The transition distance that we need at a design velocity of 70 miles an hour is 270 feet. And that's enough to because remember the car's also rotating about its longitudinal axis, even though 6% is not a lot. But you don't want to happen too fast because it'll feel like the car is being tossed up on one side. So you want to have it gradual and matching the centrifugal force. So 270 feet is not a very long curve when you consider how long our circular arcs are and stuff. So with a short distance like that, we can make some approximations for it. Now, the other place where spirals come in really handy is in cloverleaf intersections. Everybody's driven through these guys, where a cloverleaf intersection is kind of unique because in order to hang a left, you got to do 3 rights, okay? Because you're going to a transitional distance of 270 degrees, say in this case here. So the way we do that is by putting a transitional curve that goes between tangent to these 2 different directions, 90 degrees apart. If we use a circular arc, that takes up a lot of real estate, and we're coming from a very high-speed situation. Then we got to slow down quite a bit to transition all the way around. Then we have to start accelerating again. And that becomes a very sharp type of transition. In order to keep it comfortable and not have tremendous super elevation, you'd have to wind up with a very long radius curve. And now all of a sudden you don't have a very compact interchange, but you got extremely large interchange. Well, the other common way of doing it is dealing with what's called a 5-center curve. A 5-center curve is merely a compound curve, circular curves back to back. So you start off with a deceleration curve, which is a flatter curve, into a tighter transitional curve, into a tighter yet curve around here, back into another flatter curve, and then into another flat curve to do your acceleration. And if you've ever driven through one of these and try to maintain a constant velocity, you can feel it when you're going from one curve to another, because suddenly you gotta change that steering wheel to compensate for that. But you have to slow down quite a bit, and there's a lot of super elevation on this guy and through here where you're making your major directional change. Well, a spiraled curve is better because you start off with a flat, you work your way gradually into a circular arc, introducing super elevation as you're going through it, go around your circular arc, and then reverse that and come back in again on your acceleration. So your forces are balanced, and it's the most space-efficient way to make that transition between the 2 directions. So that's another place where you run into spiral curves is on transitional distances like this, or transitional directions like this on cloverleaf, or complex interchanges like this. Of course, with the DOTs, the way we're going to Wisconsin, they're turning everything into roundabouts anyway. So I don't know if you guys are getting roundabouts all over the place, but they've decided that's going to be the new thing in Wisconsin. But that's a whole other issue. Okay, so spirals. What others? Let's look at a spiral diagram. How we construct a spiraled curve based on mathematics, and some of the nomenclature in the parts. Okay, how we put all this stuff together. All right, this is directly out of the NCES Principles and Practice of Surveying Reference Handbook. That's the only book that students have available for them for the exam. Okay. Now, I think it's really interesting that they have this on there, and they also have spirals as identified in their knowledge areas for some of the things that you have to know for the exam. But they have no spiral equations on there. On the horizontal curves, they got the circular arc with the circular curve equations. On the vertical curve, they got the parabolic arc diagram with this, but they don't have any equations with this. So I'm not sure if you're supposed to be able to do calculations with this or not, or just be able to point to different parts of the diagram and say, this is this and this is that. I presume that there's some computations on it, not having taken it for a while, but I don't know. But this is the diagram, and this is typically the diagram that you see whenever you look in a surveying textbook. And if this is the very first thing you're confronted with, it's harder than hell to see what's going on, or to figure out what all the different parts are and why we've got all these different pieces and stuff in there. So let's look at starting from scratch. We kind of build our way up into a spiraled situation. And I like to use a high transition or high delta angle situation because it makes it just easier to see. So we're going over 90 degrees for the delta angle here for a traditional horizontal curve. Now there's an infinite number of horizontal circular curves that'll fit in here, but as soon as you fix the radius or the degree of curvature for it, that fixes the type of curve that'll fit in between them. So it basically is pretty straightforward. Here's your curve. Here's your circular arc that's tangent to both the incoming and the outgoing tangents. Its central angle is the same as this deflection angle here. If we want to maintain that radius, and as designers, they were balancing off centrifugal force against the geometry, and we want to maintain that radius, and we want to introduce an entrance and an exit spiral, we can't fit that curve in that same place and have spirals in it. So what happens is that curve has to shift to the inside to make room for an entrance and an exit spiral. The other thing that happens with that curve is it becomes shorter. It's no longer this length right here. And because it's become shorter and we're keeping the same radius, its central angle decreases. So instead of being delta, like it was there, it becomes something less than delta. But the angle between where this spiral begins and where this spiral ends, that total angle still has to be delta. So we've got a delta angle for the spiral here, a delta angle for the curve here, and a delta angle for the spiral here that all have to add up to that guy right there for dealing with the symmetric situation. Okay. So the way we normally define a spiraled horizontal curve is we start out similar to what we do with a regular horizontal curve. We pick a radius or a degree of curvature based on the vehicle dynamics, and we have a delta angle that we're trying to fit between two tangents. The next thing to make a spiral curve is we go to our design tables or whatever, and we pick out what's our allowable spiral length, like we had in the DOT tables for Wisconsin, 275 feet or what it was. So then we know that our spiral length is 275 feet here and 275 feet here. So once we do that, that fixes the geometry of the entire situation here. And our endpoints now become, instead of being nice, simple things like PC and PT, we now have the TS, tangent to spiral, spiral to curve, curve to spiral, and spiral to tangent. And these are all tangents, so the radii for each of the respective curves are coincident there, or collinear, same thing here, and then these are perpendicular to the tangents. And then this distance is our spiral, our tangent, our spiral tangent, and this is our spiral tangent. And that turns out to be the most difficult thing to compute about the whole spiral situation when we're working with small pieces of it. So the entrance and the exit spiral each have their own central angle, delta sub s. Those two are identical to each other because the curves are symmetric. So this curve in here becomes delta sub c, or the reduced circular curve. So the spiral angle is equal to the length of the spiral times the total deflection angle divided by 200. So we get that relatively quickly. And then the central angle of the circular arc is equal to the total deflection angle up here minus this plus this. Piece of cake. Now, when we're computing the curve part, the horizontal curve parts, we compute them just like we did before, the tangent, the middle ordinate, the long chord, the length, and all that kind of stuff. But now instead of using delta like we did before, we use delta sub c, which is this part here, because we're computing everything between these 2 points right here. Outside of that, to get from the tangent to the curve and to get from the curve to the tangent, we're now dealing with spiral components. And like I said, here's the most complicated portion of this whole thing. And this is the diagram that'll drive people nuts or make your eyes bleed if you stare at it too long. There's this thing called the offset PC, which doesn't exist. It exists only as a mathematical construct. It doesn't exist as something we stake out in the field, whether it's by the traditional method or by GPS. But the offset PC is, remember when I said when we, in order to fit this curve in here to put a spiral in here, we had to shove the curve in from the tangents. Well, if I project that perpendicular where the curve used to end, that's the offset PC. So if I were to extend this curve back from where it meets the spiral to a point where it's perpendicular to the tangent, that'd be the offset PC. And the only reason we compute the offset PC is because it's one of the components that's necessary to compute this guy right here. Because that spiral tangent is equal to all these things put together, and this is a component of all these guys right here. And the offset PC is basically that offset distance right there. So you can kind of look at that and just say, basically, this is all I got to do here. Now, so the stationing on a spiraled horizontal curve is going to be the PI station minus the TS to get the TS, plus the length of the spiral to get the spiral to curve, plus the length of the curve to get the curve to spiral, plus the length of the spiral to get the ST, and that's the ST back. The ST ahead is equal to the PI station plus the spiral tangent over here. Okay? Just an additional calculation in there that we've had before. All right, so now we got all the little pieces and stuff. How do we compute staking these things to try to keep it relatively simple? Well, we do it by we do the spiral by deflection angles. And that's similar to how we do a horizontal curve by deflection angles, by measuring an angle, a deflection angle, and a chord from the beginning of the curve to the curve point. Stake that and then go on and do the next one. We do the same thing on a spiral, except there's one big difference. When you do a circular arc, it doesn't matter which end you come from. If I take a point here and I put a tangent in here, the deflection angle there and the deflection angle here are the same because the curve's got a constant radius. But on a spiral, that's not true. If I look at my tangent to spiral and my spiral to curve, the angle between the chord and the tangent is the total deflection angle for the spiral from the flat end. That's equal to 1/3 the spiral angle as opposed to 1/2 the angle like it is on a circular arc. From the other end, that angle is equal to 2/3 the spiral angle. So that's where there's a big difference because it's a non-symmetric curve, unlike a circular arc is. So to compute, we do it one way is we get the approximate method, which is about the most common method. And we can get away with this using short spirals stuff. Basically, we're assuming that the curve is so flat and so short that the arc distance and the chord distance from the beginning of the spiral to a spiral point are the same. So that we'll say that the length from here to here is equal to the station here minus the station here. So you pick a station out on a curve, subtract the TS station from it, that's your arc/chord distance. And the curve deflects as the square. It's a proportion to the square of the distance along the spiral. So the deflection angle to there is equal to that distance divided by the length of the spiral squared times the spiral angle from that end. Bink. Piece of cake. So all we do is we just keep subtracting the TS station from our next curve point. That gives us the length. We stuck into this equation and we get the offset, the angle, the deflection angle, and the chord distance. Again, approximate. The further out we go, the longer the spiral gets, the sharper the turn becomes, the less that assumption works. It starts to fall apart. But in short spirals, we can do that. So that's the approximate method. The tangent offset method is slightly different. It's what I like to say is exactly the same, except it's totally different. In that, instead of computing directly using a direct angle and distance from the TS like we did here with the approximate, it computes a tangent distance and a tangent offset. And from the tangent distance to the tangent offset, it computes the angle and the distance. So first of all, another piece that we have in here that we didn't have before, and I left this out of the handout, so wherever this method is in the handout, I can't remember which page it's on, but I left out this equation right here. The radius to the point on the curve, the radius at any point on the spiral is equal to this equation right here, the radius of the curve times LS divided by LP. So that when we're here, the radius is infinity. When we're here, the radius is equal to the curve. Anywhere in between, it's a function of this guy right here. So we can say that the distance here to here, YP, the offset, is equal to LP cubed, this distance cubed, divided by 6 times that distance right there. Now that's kind of like the approximate method, except it's more like a Simpson's approximation. If you think about a weighted Simpson's approximation, there's always a 6 involved. So it's kind of like a power series type of thing. And then X is equal to that distance minus the offset squared divided by 2 times that distance. So that the angle is going to equal the inverse tangent of this over this for a right triangle, and then the chord distance is actually going to be slightly different than that approximate chord distance by using those coordinates. So it's a little bit more complex, but not that different when we're dealing with short spirals. The best method to compute it, and this doesn't matter how long the spiral is, whether we're using a short spiral or a long spiral, is to use the power series method. And this basically takes into account the geometry of a spiral. And this can get to be a pain in the buttocks because it's got 2 infinite series equations associated with it. So if we say the delta angle, the central angle to any point on the curve, is equal to the squared distance along that arc divided by 2 times the radius divided by LS. Then we can say that the tangent distance and the tangent offset are equal to these 2 equations right here. LP times 1 minus delta squared over 5 times 2 factorial plus delta 4 over 9 times 4 factorial minus delta the 6, 13 times 6, and so on and so forth, on to infinity. Same thing with Y sub P. It's got a slightly different power series. This one uses even terms. This one uses odd terms. So it's got even factorials, odd factorials down here. And those will give you the offsets here and here in a more exact fashion. It's not perfectly 100% exact, but it's a lot closer. Okay? And they're infinite series, so you can go on and on. But the thing is that after each series, each contributing term has less of an effect on the deflection angle. So basically, after about 4 series, after 4 terms, you can pretty much truncate it and won't make any difference, at least not measurable difference. So now once you compute the XP and the YP, then you can solve backwards to get what's your chord distance and what's your deflection angle. So you can see if you want to do it if you want to do it very exact, you do it this way, and that takes a lot of calculations. If you don't mind that being approximate or a little bit better than approximate, use a tangent offset method. But 99% of the cases, using just the approximate method will be sufficient for short spirals. Now, we can shortcut those calculations again because the entrance spiral and the exit spiral are identical. They're mirror images of each other. Now, in a traditional horizontal curve, we start stationing, we wind up with oddball stations at the beginning and at the end of that curve, and we'll stake our very first full station or first half station on our curve, then go every full station or every half station the rest of the way down the curve. Well, the spiral, to keep down our calculations and to make it easier to stake the thing, we use what are called 5-chord or 10-chord or n-chord spirals. 5 or 10 are the most common ones. And instead of going every half station or every full station, we take the length of the spiral and we divide it by 5. And then we use those as our incremental stationing out on the curve. So we wind up with oddball stations. But the nice thing about that is when I compute the deflection angles and chords for my entrance spiral, that's identical to the same spiral at the same interval staked on the other side. So I only have to compute one set of notes, and I can use it at both ends. So a 5 or a 10 chord spiral, excuse me, is the most common based on the length of the curve. The circular arc is computed using the regular deflection angle method. You know, when we're setting up the SC, sighting down towards the tangent here and then measuring off the angles and stuff. I've got a little bit more in-depth discussion in the handout on how you actually orient yourself so that you can sight tangent to this without actually having a PI up in here because you don't have one, but how you can still do that and stake that out there that way. Okay. So the way we would normally do this, the process, the traditional fashion of staking a spiral curve is starting at the PI, you would measure the TI, the TS station at the spiral tangent distance backs at the TS, sight the forward tangent, measure that same distance and stake the ST down here. Then you would compute and stake the entrance spiral from the TS to the SC. You'd back sight to the PI, and then measure your angle, your deflection angles, and your distances, and stake until you get to the SC. Then you could stake your horizontal curve, sighting here, sighting here, sighting here, and then rotating through 2/3 of that angle to make a tangent to it. Then stake your horizontal curve traditionally, you get to here. Then you go down to the ST, and using the same notes that you had here, deflection angle and distances, you're just turning in the opposite direction to stake and close in on CS here. So you're only really computing two sets of notes. One set that suffices for both entrance and exit spirals, and then one set that's for the circular curve in between. Okay. I'm not gonna mess with this. You can read that up. Already done. All right, so let's look at some example calculations here, just to kind of show you how simple or complex this can be. All right. But and this is part of the homework assignment. So you guys have all got the answers for this, right? Okay. So I'm expecting people to chime up right away. So all these little microphones that are turned off, I expect those to go off and, you know, turn on and people yell out what the answers are and stuff. Okay. So you have a 450-foot long entrance and exit spirals will be used with a 3,000-foot radius circular curve. The PI station is 52 plus 00 with a delta angle of 47 degrees left. What is the total deflection angle of the entrance spiral at the TS? What is the length of the circular curve? And what is the deflection angle at the TS to the spiral midpoint? Okay. So I'm asking total deflection angle of the entrance spiral at the TS. So I'm asking from here to here, what's the total deflection angle for that chord straight from there to there? The second question is, what is the length of the circular arc? What's the length of this guy here? And then the third question is, what is the deflection angle at the TS to the spiral midpoint? So now, if I want to know the deflection angle to the midpoint of this guy, what's the deflection angle to that guy? I got any takers on this?
Steve, Rob. There's a couple of math whizzes on here.
This is why people didn't sign up for this, is because of you guys.
They didn't want to get called out on the homework.
This is one of those things where, because everybody's got their videos turned off here, so I can't point at people and stuff. So, you know, who's in the front row and all that kind of stuff.
Jeremiah, he might have an answer.
This Rob, my dog ate my homework.
Yeah.
Of course it did.
Your virtual dog ate your digital homework, right?
Of course it did.
If there's going to be any questions on a PS exam dealing with spirals, even though they don't provide the equations, I would expect there to be bits and pieces of stuff like this, where you're just computing parts of spirals as opposed to a complete spiral horizontal curve deflection angle notes and all that kind of stuff. Okay. But basically,
How could we do it?
I'm sorry.
Oh,
George is chiming in there.
Oh, go for it, George.
I'll confess I didn't do my homework.
You think that's going to buy you any brownie points?
And I hate spirals.
You hate spirals.
Yeah, exactly.
This helps you a lot.
No, but I do know what kind of cake you're talking about. It's all the cake you were talking about was all.
You're breaking up, George.
Yeah, I was like, George, you sound like you're talking on a cell phone. You've never had issues.
Yeah, I know.
Little CB kind of guy here.
Well, my Wi-Fi is giving me problems.
Oh, there you go. Derek put in the chat about 417.50.
417.50.
Yeah.
Yeah, for the delta for the central angle. Yeah. Okay. So that's for the central angle. The total deflection angle is 1/3 of that. So that's a spiral angle. Then remember, at the flat end, it's 1/3 of the spiral angle. At the other end, it's 2/3 of the spiral angle. Okay. Right. So the next one is, what is the length of the circular curve? Well, now you know that. Now that you know this angle here, you subtract twice of that from the delta angle to get the central angle of the horizontal curve. Then once you've got the delta angle, once you get delta angle horizontal curve, then you can use the regular curve length equation to compute the length of the curve, 210.90.
I bet you Derek got that. I bet you Derek got that too.
I gotta look at the chat.
Oh, you're okay. Yeah, there's a couple. Jordan says I was at work and then getting the truck serviced.
There's also, I had one student once told me that she didn't get the assignment done because there was a tornado on her street last night. That was interesting because I live in the same town. I don't remember seeing one. Amtrak says, nerd. Who's a nerd? All right.
I think that was to Derek because he got the right answer.
No, that was to myself when I said I love math, and then Derek had answered, so I realized that it sounded like I was like hating on him. I love math.
All right. Well, then, what's the answer to the third one? What's the deflection angle to the center point of the spiral? Because that was the third one, right? Da, da, da.
Hold on, Derek's calculating.
Derek's calculating. Okay, I'll let it go. Well, I'll throw this one up here. The deflection angle to the midpoint, distance is half the curve length. So 225 over 450 squared. Remember that it's a square. It functions. It's as the square times the deflection angle at the flat end. So it's 21 minutes, 29 seconds. So it's relatively flat. The further you go on it, the sharper it gets. Okay. All right. Let's see. Let's look at example 2. A 300-foot long spiral will be used with a 3-degree circular curve. The PI station is 40 plus 0, 0. The delta angle is 60 degrees to the right. Using the approximate method, compute the 5-chord deflection angles notes for the spirals. So it's a little bit more involved, but basically, remember we're doing the approximate method is this guy right here. We're just doing the distances, and we're using 5 chords. So you're taking the length of that spiral, dividing it by 5, and that's how many stations out on, how far out on the curve you're going to be going. So you're going to be going those increments, and those increments are going to be how much LP changes each time. So if it was what was the length of the curve? 300-foot long, 5-chord spiral, so it's going to be every 60 feet. So LP is going to increase by 60 feet. So you have 60 over 300 squared times the deflection angle at the flat end of the curve, which is half of the delta angle, or one third of the delta angle for that spiral curve. Got that? In English. Okay, let me show you. Delta S, we have to figure that out first. That's equal to the length of the spiral times the degree of curvature divided by 200, which means that the central angle for the spiral is 4 degrees, 30 minutes. The circular curve central angle is 51 degrees. Okay. When we're looking at the 5-chord spiral, and we've got a 600, we have a 300-foot curve, we're going to take 300 divided by 5, gets 60 feet. So our equation for our approximate deflection angle is the distance out on the curve divided by LS. So this is going to be 60, 120, 180, 240, 300 over 300 each time, times delta S over 3, which is at 4 degrees, 30 minutes. So the distances themselves are just going to be those incremental distances. So we're going to have 60, it's going to be 336, 120 is going to be 1424, 180, 3224, 240, 5736, and 300, 1 degree, 30 minutes. Then you notice that the angle gets bigger the further we go on. I mean, it increases at a growing rate as we go on. It's not a constant rate because the spiral gets sharper the further out you go on it. Now, because I computed that as a 5-chord spiral, I can stake the entrance spiral from the TS using these, and I can also stake the exit spiral from its flat end using that. I'm just turning, in one case I'm turning to the right, in the other case I'm turning to the left, but same deflection angles and the same distances. Okay, back to example 3 now. One more here. 275-foot long spiral will be used with a 2,500-foot radius circular curve. The PI station is 63 plus 0, and the delta angle is 38 degrees. Determine the curve system endpoints. That's basically what's the TS station, the SC station, the CS station, and the ST station. Anybody get those computed?
Doesn't look
Oh,
like
yeah, sure. You're pretty cocky there at the beginning there, and now all of a sudden you start to drop off. Huh? Let me see. These were part of the assignment, so this
Derek,
one lost. This one
yeah.
lost me.
Derek said lost.
Spiraling out of control. Okay. Whoops. You still see? You still got my PowerPoint up there, right? Not my. I'm dicking around here with some stuff.
No, yeah, we see your PDF at the moment.
Oh, okay. Because I'm trying like, yeah. I can't get it because that stupid little thing up at the top there move.
Yeah, the viewing. Yeah.
Okay, so I can't grab the top. I hate that when that happens. Okay. So that right there, determine curve system endpoints. Okay. Spiral out of control. Yep, but I'm bump. Thought I had it. Derek says, thought I had it. What'd you have, Derek? Let's look at the solution. Okay, first of all, figure out the central angles. We got to type the degree of curvature, and then we figure out the spiral angles. And so the spiral and entrance and exit spiral angles have got 3 degrees, 9 minutes, 4.6 seconds, which means that the central angle for the circular arc is 31, 41, 50.8. And with that, we got to compute the curve length, and then there's all that crap that we figure out in there. Okay. There's the curve length. This is that TS spiral tangent. We got to figure out all these other guys here to come up with that spiral tangent of 998.77. All those calculations for that sneaking number right there. So then our station of TS is equal to PI station minus that. Station of TS, station of SC is that station plus the length of the spiral, 275 feet. Then the station of the spiral to curve, or the curve to spiral, is equal to that plus the length of the curve, which we computed here. And then adding the length of the spiral gets us back to the ST, the back station. And then the ST ahead station is the station of the PI plus that spiral tangent. Everybody knows what the difference between the back station and the head station is in alignments. People don't use that so much anymore because everything's digitally designed nowadays and stuff. But the head and the back station made up for the discontinuity and the distance differences going up and down the tangents versus around the curves. Okay. Little historical thing. Supervise this anymore. Yeah, that's why we have software to do it. Okay. All right, let me throw up now. I get my PDF up here, and we can look at the rest of the assignment answers, and then the assignment questions, and see if anybody else venture to answer for these. What advantages are there, if any, for using spirals? Who wants to give me some advantages for it, if there are any? Besides, they're fun to compute.
Said no one.
No one's gonna venture a guess on that one.
Takes less area because you manage the force more quickly.
Yeah, it's a and that goes back to its force balancing nature, going back on vehicle dynamics. So it's less space, you can make for more efficient large transitions. And that kind of leads back to what its original intent was just in general introducing super elevation rate to uniformly offset the increasing centrifugal force acting on a vehicle. So it's in these days of really flat curves and stuff like that, you don't really need them that much, but for shorter curves and sharper curves, they make a nice transition. How's the offset PC defined? Remember what that was?
The distance from the tangent line to the point where the radius of the circular arc is parallel to the radial line of the tangent spiral.
Yeah, okay. Yeah. You can also think about it as when we push that curve to the inside so we can fit the spirals in there, it's the PC has to get shoved in that perpendicular distance in order to make that spiral. So the longer the spiral is, the further that distance is. Yeah. Question: blank is inclining the pavement in order to use a complement of this vehicle's rate to offset what? So with the blank, question number 3, blank is inclined to pavement. George, you're either gonna have to speak faster or
Yeah, your Wi-Fi's kicking your butt.
yeah, it's yeah, sneak that in there.
Okay, I'll go really fast. The big advantage is doing roads in mountainous areas where you don't have much room.
Yeah. Yeah, his Wi-Fi is really slow. He's 3 questions behind us. Okay, we're on question 3 now. Blank.
So I know that, but
yeah, blank 1 and blank 2. What are those?
Cambering and lateral.
Super centrifugal force.
Right, there you go. Super elevation and centrifugal force. All right.
There you go.
Entrance spiral starts with a radius of
larger value.
And what is that value? It's always the same, regardless of how long the spiral is or what the curve situation is. It always starts out with a radius of infinity. It always starts out with a radius of infinity because it starts in a straight line. And then what it ends at is going to be a function of the design of the curve, but it always starts with a radius of infinity. And these other guys, yeah, these other guys are just the problems we worked out here. So that's the value added part of the vector. What I do want to point out, though, is one of the things I do have on my website is a spreadsheet. And I actually have that spreadsheet. I have so many windows open here. Ding, 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 right there. right there. This is the spreadsheet on my website. And it's kind of hard to see all in one because I tried to cram as much of it onto one sheet as possible. But basically, there's a little instructions thing that tells you what to put in there and that type of thing. But you input your PI station, your total deflection angle, and the radius for your circular arc, and your spiral length. And the entrance and the exit spirals are going to be the same. You input all that, and then what it does is it computes for you by the approximate, the tangent offset, and the power series methods, what the deflection angle and the arc distances, the deflection angle and arc distance. So it does it for a 5-chord spiral and does it for a 10-chord spiral. So you could take these problems we were working on tonight, throw those stuff in there, and they'll give you the answers for this. But you can see that, let me look at this 5-chord spiral one, for example. For this combination of numbers, when you get to the end of the spiral, this is from the flat end to the sharp end. You can see that the angle goes 31.35, 41.3, 20.2, 1.5. These are pretty close to the same. And these are pretty close to the same. These are the more exact ones. So you'll see a little bit of differences, but there's not much because the spiral is not very long. If you were to stick a huge long spiral in there, then you'd start to see differences out in these guys here because those initial assumptions on the flatness of the spiral and using the arc as a chord calculation starts to fall apart. But if you keep the spirals relatively short, we put a 500 foot in there once and see what happens. Yeah, you start to see a difference here. There's 35.5, 36.8, and 34.9. It starts to get different when you get to the ends of those. So the longer the spiral is, the more the approximate and tangent offset method fall apart, and the power series becomes your way to compute it stuff. So, but usually you don't work with 500-foot long spirals. Okay. All right, that's what I got. I want to get that through as quickly as possible tonight, and just kind of touch on the basic math and the geometry of spirals, and talk a little bit about some of the calculations and stuff. Do you want to mention that? Yeah, the railroad spirals are based. Yeah, says there that George says that the railroad spirals are generally based on a 100-foot chord. That's correct. They use chord distances, chord definition, as opposed to arc definitions like we're using highway work and that type of thing. But when it comes to the actual spiral calculations, the spiral calculations themselves for the non-curved part are basically the same because it's still the assumption that the chord and the arc distance are the same. Okay, so the actual calculations of those are the same. And as a matter of fact, the 5 and 10 chord is a really common type of spiral to use, or common type of way to compute spirals in railroads. There's an area spiral, AREA. I'm trying to remember what it stands for. There's a particular type of spiral that's used a lot in railroad work, though the geometry is slightly different. It's American Railroad Engineers Association, I think it is a definition that they came out with, a spiral that they use. Bay Area Rapid Transit System, when that first came in back in the 70s, was the first place that really got into high-speed rail in a big way in this country here, and got into spiral curves and that type of thing. And they used the area spiral for that. Okay, I'm looking to see if there's anything else that's in the chat that I haven't answered or confused any further than I have. Though, are there any questions on this in general?
There's a lot. I see Steve, you got something? You're unmuted there, but
There's a chatter. This makes sense for a satellite calculation. What's the purpose of assigning spiral curves along the edges of right of way? In a lot of cases, from a lot of the railroad stuff I've seen in Wisconsin, they don't use spirals for the edges of right of way. They use spirals for the center, for the track, center line of the track, but for the actual right of way calculations, they use circular arcs that give you a corridor large enough that the spiraled curve fit in between. And that was, I think, to help keep the calculations relatively simple on the offsets for land acquisition purposes. A spiral is a pain in the butt to try to do an easement definition when you're offsetting your center line so many feet on both sides, because it changes the spiral geometry. Not just that, like on a circular arc, you're increasing or decreasing the radius on a concentric curve, but on a spiral, it's not the same. It doesn't everywhere decrease it by 30 feet along the length of the spiral. So it's a little bit more complex.
Yeah, there was a railroad.
And beyond Alaska shows, okay, that's probably a little bit more contemporary than a lot of some of the CONUS type of stuff, some of the older railroad stuff that we have in this, at least in Wisconsin. Our stuff dates back to the early the early to mid 1800s and stuff. How can you say that again? How to figure railroad right-of-way arcs? Which part? Because I just said a lot of stuff that most of it was gibberish. No, what I'm saying is when you offset,
offsetting it.
yeah, when you're offsetting, say, when you're doing a regular alignment where you've got a circular section with tangents on both sides, and you're offsetting at 30 feet on both sides for a 60-foot right of way, your arcs and your geometry are maintained throughout. Okay. Whereas with a spiral, because the spiral has got a varying radius on there, when you offset at 30 feet, you're actually changing the geometry of the spiral somewhat. So rather than come up with a whole other set of calculations for those, a lot of times what they used to do was just use circular sections on the inside and the outside to define the right of way and just fit the corridor, the spiral in between there. So it would fit in that corridor. What really, when we, and I'm sure a lot of other states have done this too, where you have the rails to trails type of programs, where when they pull out the railroad tracks and stuff, they don't monument them ahead of time when they pull them out and all that kind of crap, because they use the rails as their monuments and that type of thing or whatever. To try to figure out where the edges of the right of way are based on spirals is a pain in the butkus. So it's easier fitting circular arcs to define where those right of ways were than trying to do spirals. Railroad companies were notorious for destroying the old records and stuff, or when they got bought out by other rail companies and stuff, just saying, we don't need all this old crap, let's just throw it away, burn it, make kindling out of it. But questions were there. Okay.
I really appreciate the calculation sheet, because there are times where I have to use that for highway retracement and figuring out where the station of a particular monument is, because there are spiral curves. But
yeah, okay, good.
On the same note, it's important that when you're looking at the conveyance document for that corridor, that you're reading it carefully. I had a surveyor whose work I was reviewing misinterpret the deed and assume there was a spiral curve on a course, because the official map for it showed a spiral curve along the center line, but it was actually just a straight line that connected the two tangent points together. It was just this strip off to the side of the right of way. So we spent too much time, I won't go into how much, trying to figure out what the spiral curve would be, but it was irrelevant because I didn't have the deed, so I didn't know. But once I got the deed, I read it and was like, wait a second, all it says is along the chord, and the chord is this bearing and distance, and that was it. So
that's all. Yeah, that's all I was saying before, that they simplify the actual right-of-way edges, even though the rail itself might be a spiral situation. They try to simplify the other stuff to make it as easy to describe or to lay out as possible.
forest for the trees on that one.
Yeah, well, that's why I always tell my students, charge by the hour.
I was doing a couple searches, and looks like there was some stuff from Wisconsin about railroads. There's a couple of PowerPoints out there.
Yeah.
Railroad Surveying 101, and it's a three-part PowerPoint. But
yeah, we had representatives from the rail industry come in and address the Wisconsin State Land Surveyors a number of years ago and talk about some of the basic terminology associated with rails, as well as the geometry and that. We do have our commissioner of railroads within the Wisconsin Department of Transportation that maintains a lot of the records and connections with the rail industry, and the Southwest chapter of WSLS actually went through and scanned all the old railroad records for the state of Wisconsin. So we have those on CD now, or on DVD, that you can call up all the old plans and stuff and look them up. And they're all indexed by regions of the state, which is kind of neat. We happen to have those kinds of records that are still maintained in the Commissioner of Railroads office. I don't know if other states have got that or not, but it's a damn good resource, particularly with the rail and trails type of thing. With ATVs becoming really popular now, we're putting in recreational trails all over the place, and you want to be sure that you've got them in the right spot. You know, like I said, once the rails are gone, that's your primary physical monument that's out there. So, there's always Steve Martin says, I went to a railroad seminar where the speaker said railroads are based on simple curves. That contrary has been shown. There's always going to be a contrary. There's always going to be exceptions to the rules and that type of thing. So like I told my students every time I taught a legal course, the answer to your question is it depends. You know, so but there's going to be all sorts of variations too. That's why just like anything else, you got to research the records. You know, I mean, don't just assume that, like in the case that Steve was talking about, that because the rail was laid in with spirals, that automatically the right of way is going to be laid in by spirals. Go back to the legal document. One's a numeric, one's a geometric document. The other one's a legal document. Oh my God, look at all those links. I could not follow what it was like. It was really complete. You're welcome. Okay. Anything else here? I'm in the process of updating a lot of the material on my website. Now that I'm retired, I have all this free time on my hands. So I will be updating some of the spiral stuff on there. Some of it's a little bit dated, but feel free to look at that stuff and see some more additional explanation and diagrams there, and as well as a spreadsheet that's available at the site there. If you have any questions on any of that stuff, let me know.
I did download it and throw it in the Dropbox for this particular week as well.
You might have to, because Microsoft has gotten a little bit more touchy on security on things that get downloaded from the internet. If you try to open it and run it, it may give you an error statement because, one, it uses Visual Basic to do some of the calculations, and two, because it's downloaded from the internet, Microsoft is becoming the nanny state. So you might not need to change. You might need to change the security on the file in order to be able to open it and run it. There'll be a little banner that'll come up to tell you how to do that if that's the case. But I downloaded today and it seemed to run okay.
This product is not warranted against defects or errors by the author.
That's right. That's me. And it's supposed to be used for educational purposes, not intended as a production product.
Right. Great as always. I don't know if anybody has questions. There's been a little bit of chat back and forth, but
yeah. There's some lot of good links in there, it looks like. So that follow up on those. And like I say, if anybody has any questions on any of this, particularly those of you that may be studying for the FS exam and have just more questions on basic calculations and stuff, and you can't get the questions answered on my website or anywhere else, feel free to drop me an email, and I'll be more than willing to respond or even meet with you online or something, discuss the things with you.
Yeah, no, that was awesome. I love it as always. Next week I'm at Geo Week. Oh, somebody's coming in at the last second. And then President's Day weekend. So I'm trying to get Dane Corville set up for the 26th of February. He's working on one right now. So 2 weeks off, but then we'll be back. So I love it as always. Anybody else?
If anybody that's taken the exam wants any more particular topics covered that help with the exams, let me know.
Yeah, exactly.
And we can put that together for you.
Thanks, Jerry. You're a rock star.
As always,
Hey.
exactly. I love it. All right, everybody.
All right.
Have a good week.
Thank
Thank
you
you,
for
Jerry.
coming. All right. Good night.
Bye, guys. Thank you.
Hey, Trent, I'm going to call you.
Okay.
Goodbye.
All right. Bye.